Hi, in this video we are going to look at how to do chi-squared test, which is the sixth part of Jamovi. So here we're given some data on color frequency of M&Ms in a bag. This is the data that we'd used in an in-class example, and we want to test and see if it follows this distribution. 24% were let's see, blue here, 20% orange, 16% green, 14% yellow, and 13% red. So remember, when you're trying to test if your data here fits a distribution, that's the chi-squared goodness of fit test, GOF. So in order to do that, you want to go to frequencies here, and then you're going to come down to end outcomes. See, it says chi-squared goodness of fit. You're going to click on that option here. We will put color as our variable and then frequency as our counts. We are also going to check the box expected counts. So for each color here, we've got the observed, the actual number that were in the data, and then what we would expect if the null hypothesis was true. So remember, the null hypothesis is that the data does follow the distribution. The alternative is that it does not follow the distribution. So, and then down at the bottom here, we've got our chi-squared test statistic of 13 and our p-value of 0.011, which is less than 0.05. So here we would reject the null hypothesis and say that these colors here do not follow the distribution that we were given. Now, in the project itself, you're going to be working with the data file graduation 2019. You're going to be seeing if the distribution of honors, no honors, cum laude, magna, and summa, you're seeing if that follows a distribution. So you'll list your observed and expected counts, your test statistic, degrees of freedom, and p-value. So observed and expected in this first table, test statistic, degrees of freedom, p-value. So that is goodness of fit. The other chi-squared test here, remember, is the test of independence. So, and this is really a test of association. So you want to test and see if the variables are associated with each other. So let me go ahead and get rid of this output, show you how I got it. So what we have here is we have age groups, young, middle-aged, and older adults, and then we're looking at the number of recyclers and non-recyclers in the group. So in the young age group, there were 77 who recycled, 32 who did not. In the middle age, 65 recycled, 36 did not. And the older age group, 54 recycled, 46 did not. So what we want to do is we want to see if there's any relationship between age here and recyclers, proportion of recyclers. So we want to see if they're associated or related. So in order to do that, you're going to go to the Frequencies tab. You're going to go down to Independent Samples, chi-squared test of association. So click on that. We'll put age group as our rows, and then the recycling status as our columns. Counts are in the frequencies, are in the recycler column, right? We go back to our data here, recyclers. So maybe I should just put count there. And let's see here. Well, I want to let me get rid of this and go back and redo it. So again, frequencies, independent, ages are row. Recycling status is our column. The counts are in the recyclers column. And then under cells, we want to check not only observed, but also expected. So now we've got observed and expected in the young age group. So we've got observed and expected number of recyclers and non-recyclers. Same for middle and older age group. Test statistic, 6.29, degrees of freedom 2. p-value 0.043, which is less than 0.05. So we would reject the null hypothesis. So the null hypothesis is that age and recycling status are not associated. The alternative is that they are associated. So what we're seeing here is that recycling status does change with age. And then what you're going to do in the actual project, you're going to be working again looking at graduation honors distributions here. You're going to be looking at year versus honors categories. You're going to fill in your observed and your expected from the results here with the data for the problem, not this data. And then you've got your chi-squared degrees of freedom p-value, which are going to go in here. And then your decision, reject or do not reject H0, and then what does that mean? And then you're going to look at the cells and their cell contribution to see how much each cell, the expected, differs from the observed. So that's your explanation here. So you're trying to see which cells provide the most disagreement, the largest contribution to the chi-squared test statistic. And then you're going to redo the data with 4 years instead of 2. So redo the experiment again with 4 years instead of 2. So we should be able to do both a chi-squared goodness of fit and a chi-squared test of independence with Jamovi.